Hello everyone. This is part 2 of section 7.1 where we looked at the p-value method for hypothesis testing and we saw the 5-step procedure. Recall there is the formula sheet which gives us our formulas for the test statistic Z and tells us the conditions when we know sigma and the sample is random and either normally distributed or n is greater than or equal to 30. Also, that information is contained in this little flow chart as we mentioned last time. Makes it a little bit easier to just distinguish it. Do you know sigma? And so on. And also this is the cheat sheet for your final exam that I mentioned, and there's the procedure for both the p-value method and the critical value method, which we're going to look at now. And also on the side here is how we rate our conclusions based on our decision, which is in the left here, either always with respect to HO, either reject it or fail to reject HO, and depending on what the claim is, then this is how we would rate our conclusions. So we saw the p-value method, now the critical value method. And this is the most commonly used method, although p-values are what many statistical reports will give in terms of an interpretation. But the critical value method is used more widely, and with the critical value method, basically the only difference, there's 3 steps are the same. That is, our first step stating the hypotheses, identifying the claim, our 4th step with regard to decision, but it's based on the critical value rather than the p-value, and then our conclusion, so those steps are all the same. And then the 2nd and 3rd step are a little bit different because we're looking for a critical value rather than a p-value. So we have what we call the rejection region, and that's when the null hypothesis is going to be rejected. It's not very probable that it will occur if the test statistic falls in the rejection region. And the critical value separates the rejection from the non-rejection region. So we have a good region and a bad region. And here are the guidelines for finding the critical value. We need the level of confidence, and we need to know what type of test it is, left tail, right tail, or two tail. And a little summary of how you can go about finding the critical value, which we'll call Z sub C. This we can almost do intuitively. You really don't need formulas for it. But if you like the use of the formulas, that's fine. And we're always going to want to sketch and make sure we shade the rejection region, and that will help us through the region or regions if it's two-tailed, and that'll help us through the process. So when we make a decision, and this is almost intuitively obvious, we first find the rejection region, and then we get the standardized test statistic, and if the standardized test statistic is in the rejection region, then we reject HO. And if it's in the non-rejection region, we fail to reject HO. So non-rejection, fail to reject HO, and rejection, reject HO. And so before we get to the actual procedure, the 5-step procedure, here is a quick example of finding the critical values. And so we'll call them Z sub C, and we're going to make a decision to either reject HO or fail to reject HO based on the standardized test statistic that's given. You always want to make a sketch of the normal distribution. And it's a right-tailed test, so therefore we'll have, okay, you could always put z equaling 0 down the middle, of course. We'll have this right tail represent the critical value, and we'll shade in the rejection region. Now, the level of significance alpha was given to be 0.01, and that's the area in the tail or the tails. But to find this z-score, we need this left cumulative area, and that's the complement. So we calculate 1 minus, of alpha that is. So we calculate 1 minus 0.01, and we get 0.99. Let's add a couple zeros, and then we look that value up in our table. Remember, this is going to the guts of the table. So just to remind you of this, we're looking for 0.9900. So we look in the guts of the table, and closest one looks like 9901, which is 2.3, and then reading the heading on the top, 03, so 2.33. So that's our critical value. And then using the test statistic, just determine where it falls, where the test statistic falls based with respect to the critical value. And 1.78 is somewhere in here, which is in the non-rejection region, and therefore we're going to fail to reject the null hypothesis. Okay, so let's draw another. I'm going to put the diagram over here to give a little more room on the bottom for the labeling. But now we have a two-tailed test. So we have a tail on the right, a tail on the left, two critical values. Call it z sub c and negative z sub c, I suppose, if you wanted to, but just want to identify those critical values, shade in the tails. Those are the rejection regions. And as we've done in the past, if we have z-scores that are symmetrical about the mean of z equaling 0, then it's easier to work out the z-score on the left. And if alpha is 0.05, that represents the area in both tails. So the area in this one tail is alpha divided by 2. 0.05 divided by 2, which is 0.025. And I'll add a 0. And then we'll go to the table, and we'll look that up. And we get negative 1.96. And so the positive z-score would be 1.96. So if you wanted to say z sub c, like up here we could have said z sub c is 2.33. And the rejection region, sometimes MyMathLab asks you, let me state this, the rejection region would be z is greater than the 2.33. So here z sub c is equal to either plus or minus 1.96. So sometimes MyMathLab asks you for the rejection region. So the rejection here would be z is less than negative 1.96, or z is greater than positive 1.96. That just describes the two rejection regions in this case. So sometimes MyMathLab asks you for the answer that way. But I think drawing the diagram's nice, because then all you have to do is locate the standardized test statistic that's given, or that's calculated, as we'll see. And with respect to our z-scores, negative 2.84 is somewhere over here in the rejection region. And so therefore we reject the null hypothesis, HO. Okay, so now we're ready for the actual 5-step procedure. It's summarized there, also summarized on our cheat sheet for the final exam. And as I had mentioned, if you look, steps 1, 4, and 5 are identical, and steps 2 and 3, the only difference, instead of calculating the standardized test statistic first, after stating the hypotheses and identifying the claim, for the critical value method, we determine the critical value first, and then we calculate the standardized test statistic, and then we make our decision based on where the standardized test statistic falls with respect to the critical value. So, as always, we're going to write the givens off to the side. We have to decide Z or T, even though right now we've only studied Z. We have to remember in Chapter 6, we're going to have to worry about the T distribution at some point. But the givens are typically going to be the same. This light bulb manufacturer makes this claim that their mean life, so now we're talking about mu, the population mean of these life of these light bulbs are at least, so at least means greater than or equal to 750 hours. So that's going to be the state your hypotheses and identify the claim. That is HO, HA, and greater than or equal to contains equality, so it goes with the HO, the null. So mu is greater than or equal to the 750 is our claim. And then HA would be the complement. Mu is less than the 750. Okay, and then continuing, random sample with 36 light bulbs. So N is 36. Their mean life, so this is coming from the sample of the 36 light bulbs, the mean of that sample, so that's X bar, our sample mean is 746. And from past studies, remember, suggest the population standard deviation, so sigma is 10, and then at alpha equaling 0.02, what do we say about the claim? So based on this information, in particular, nothing's mentioned about being normally distributed, but we do know sigma and n is greater than or equal to 30. And so therefore, if you use your flow chart, or if you use the characteristics that are described in the formula sheet, the flow chart's nice and easy to use because do we know sigma? Yes, we do. So check for normally distributed. Didn't say anything about that, but n is greater than or equal to 30, so it tells us to use Z. So this tells us to use the Z distribution or the normal distribution. Okay, we already stated our hypotheses, identified the claim. Next step, critical value. And that's our formula. Z is X bar minus mu over sigma divided by the square root of n. X bar from the given is 746 minus, and then always remember that the value of mu is the hypothesized population mean. So look at your hypotheses, and that's 750 in this case. And then over sigma, the given was 10, divided by the square root of n was 36. So crunch that down, negative 2.40. Oh, I'm sorry, that's actually the standardized test statistic. I switch these steps up. That's step 3. Step 2 is the critical value. I apologize for that, but no big deal. So for the critical value, withdraw the distribution. So I switched these steps around by accident. I apologize. But we'll continue with this. And we put Z down the middle. What type of test is it? Remember, that's based on the inequality symbol in HA, the alternative. It's less than. So therefore, one-tailed right-tailed test. So it's a right-tailed test. So we draw a tail. That's going to represent Z sub C, the critical value. And alpha is the area in that tail. So this area is 0.02. Add a couple zeros. Look that value up in the table. Again, in the guts of the table, find negative 2.05. And so Z sub C is negative 2.05. And you could say reject when Z is less than negative 2.05. And we already calculated our critical value. Negative 2.4 is in the rejection region. And so therefore our conclusion, and since HO was the claim and we're rejecting HO, there is enough evidence to reject the claim. I'll just put the little ellipses there. Okay, a couple more examples to go over. I apologize for switching these steps, but make sure I do them right in the next 2 examples. Oh, and the conclusion, once again, you could be using your little table here, where our claim was HO, and we rejected it, so there is enough evidence to reject the claim. Okay. All right, so a couple more examples. And now we have a random sample of 85 8th grade students. They have a mean score of 282 on a national math assessment. So N is 85, our sample size. So sample's 85. This is the mean coming from the sample. So that's our sample mean X bar. And it tells us the standard deviation of the population, so sigma is 35. And an administrator declares that the mean score of his 8th grade graders is more than 275. And so that has to do with the claim. And more than represents strictly greater than. And so we're also given that alpha is 0.04. And now based on the given, we know sigma n is greater than or equal to 30. So we're going to use Z again. Alright, so the hypotheses, HO, HA. He states that they're more than or greater than 275, and he's talking about the mean score, so that represents mu, and strictly greater than goes with the alternative, so mu is greater than 275 is the claim, but the alternative again, so mu is less than or equal to, the 275 is the null. critical value. So we go to the critical value next, and we draw the distribution. Now, this is a left tail test. Because again, we look at the inequality in HA, it's greater than. So we shade in that region. Put Z equaling 0 down the middle if you like. But this is going to represent the critical value. And the area in that tail is the value of alpha. So alpha is 0.04. But to find the critical value, we need the area to the left of that, which is the comment, 1 minus 0.04, or 0.9600. And then we look that value, 9600, up in the guts of table 4, and we find 1.75. So then we go to our test statistic. So our test statistic is Z equaling, again the formula is x bar minus mu over sigma divided by the square root of n. X bar from the given was 282. Remember, always mu is the hypothesized population mean that is associated with the hypotheses. And so 275 in this case over sigma 35 divided by the square root of n, which in the given was 85. So that gives us a z-score of 1.84. So then we just compare that z-score to where, remember the shaded region is the rejection region, so where does 1.84 fall with respect to the critical value of 1.75, and it's somewhere over here. Z equals 1.84 is in the rejection region. So therefore we reject, and remember always your decision is with respect to HO. And then we could draw our conclusion, use that little chart if you want to. If we're rejecting, I'm just going to do it intuitively though, and you could check the chart on your own. If we're rejecting HO, that means that HO is the bad thing. What I usually do is I cover it up, and that leaves the claim as the good thing. So therefore, and remember, with if HO is the claim, we use the word reject in this conclusion, and if HA is the claim, we use the word support in the conclusion. So since the claim is okay, there is enough evidence to support the claim. So as I said before, it might be nice when you solve the problems in MyMathLab to actually go through this 5-step process and then to look at the way that they ask the questions, because they could ask the questions in a slightly different manner. So maybe just following a standard 5-step procedure is going to be the best way to proceed. Okay, so one more example. And here it's claimed that the mean weight of female students at a particular college is 54.4. So is suggesting equals. We're going to test the claim. We get a sample of 100 weights of females. Okay, so let's do the givens off to the side. The 54.4 has to do with the claim, of course. And we have that sample's 100. Tells us the sample mean, so it literally says that. So X bar 53.75. Previous study, remember, is the population standard deviation. sigma 5.4, and can test the claim with a level of significance alpha of 0.10. Alright, so we know sigma n is greater than or equal to 30, so we're going to use z. Alright, so the first step, once again, hypotheses, identify the claim, HO and HA. We're talking about the mean weight, so that's mu again, is equal to 54.4. So since it contains equality, it goes with HO, the claim. So mu is equal to 54.4 is our claim. And that means the complement mu is not equal to 54.4 is the alternative. Next up, the critical value. So we draw our distribution. And because the inequality in HA is not equal to, it's a two-tailed test. So we draw two tails. Again, you could put z equaling 0 down the middle if you like. So here's z sub c, the right critical value. Here's z sub c, the left critical value. Shaded in those tails. They represent the rejection region, regions. And alpha is 0.10, but since it's two-tailed, we can work out the left tail, and the area in that tail is half of that. 0.10 divided by 2, or 0.05. Add a couple zeros. Look at the 0.0500 up in the guts of the table. Here you find, remember this situation sometimes arises, and so when I look up 0.05 in the guts of the table, I find that I'm right well, let me see, 0.05 is right here. I find that I'm smack dab in the middle between 0.0495 and 0.0505. So therefore we split the difference in 1.6, and then we're between 0.04 and 0.05, so we'll say 1.645. So negative for the left and positive for the right. So you could say z sub c is plus or minus 1.645. And, you know, if you had to describe the intervals, you could, like we did earlier. Okay, then the test statistic. So z formula again, x bar minus mu over sigma divided by the square root of n. From here we just plug in the values. Sample mean x bar 53.75 minus mu, once again the hypothesized population mean from the hypotheses, 54.4, all over sigma 5.4 divided by the square root of n, is 100 in this case. So we get negative 1.20. And so we place that on our sketch, and that falls in the non-rejection region. Okay, so it would be somewhere here. Z equals negative 1.20, so between 0 and negative 1.645. So therefore our decision, because we're in the non-rejection region, would be to fail to reject HO. And then we draw our conclusion. And so if we're not rejecting HO, that means that HA is the bad thing. The word reject is always in our answer if HO is the claim. So there's not enough evidence to reject the claim. And again, you could be using that little chart. So I'll just remind you of that little chart. I think we've done it enough, but again, it's on the little cheat sheet for the final exam. Squeezed in there. Claim is HO. We're failing to reject it. Not enough evidence to reject the claim. So that's, of course, what we wrote intuitively. Little note to just finish off concepts here, just to mention it. The difference is between p-value and critical value is we compare a p-value to alpha, but critical value, we compare the test statistic to the critical value. And so the p-value is found from the test statistic, but here we just get the test statistic and we compare it to the critical value, and that's how we make our decision. Okay, so that's the end of section 7.1.